Okay, in the previous video we talked about 2D parametric curves, what they were and how to visualize them. Now we're going to talk about 3D parametric curves. So recall that these parametric curves mean that instead of having an equation relating x, y, and z, we have x as a function of time, y as a function of time, z as a function of time. T is usually what we call that extra parameter, and we think of it as time, because for any fixed time, this tells you a specific x, y, and z coordinate. For instance, this red dot here may represent the case when the time is equal to 0. So I don't have specific formulas written here, but you might think of this as, who knows, maybe that's going to be x of 0 equals 1, or 0, let's say, y of 0. I mean, it's hard to tell exactly where that red dot is, but then that would be z of 0. So the point is, plugging in t equals 0 into these formulas would give you specific numbers here, and it would tell you that's where you start at time t equals 0. As you let time march forward, x, y, z change, so your dot is just going to move around in certain directions, wherever in the entire xyz three-dimensional space. In the process, it would trace out some kind of, if I can draw this, it would trace out some kind of weird trajectory just like that. And this is very useful in physics, where this actually would be a particle and you would look at it as its trajectory. Okay, so let's get a better idea of how we can actually visualize it. For instance, let's take a look at a specific example. What if x is cosine of t, y is sine of t, that should be similar to what we did in the 2D case, and then z of t is just t. So at t equals 0 in this case, we would be at the point, well, I guess cosine of 0 is 1, sine of 0 is 0, and of course t is just 0. Then at t equal to, say, pi halves, it would actually be cosine of pi halves is 0, sine of pi halves is 1, and, well, that's just t, so that's just pi halves for the z-coordinate. So you'll notice that as t gets bigger, since the z-coordinate is t, it's getting bigger too in this specific case. By the way, this picture here does not represent that simple little formula that I just drew. This is something probably far more complicated. Here, as we'll see in just a moment, what I'm describing by this specific equation is actually going to be a nice kind of helix shape, something that looks more like a coil or a spring. We'll see that in a moment. Well, actually, let's see it right now. I already have it plotted here in Microsoft Math. So here's the equation x cos t, y sine t, and z equals t. And you can see that it's just, as t increases, you're kind of going up the z-axis, but otherwise you're just kind of wrapping around the y and x as if you're just going around a circle. So in fact, you can see that when the z is pointing directly at us, it's stabbing the viewer in the face right now. The x and the y seem to just be going around and forming a circle, which is exactly what we had for x cos t and y sine t when we were graphing it in the plane. Similarly, and I'm going to try and now show you so that the y is stabbing you directly in the eyes, it looks like a simple sinusoid. And if I try and get the x to stab us in the eye, then it also looks like a perfect little sinusoid just like that, or some kind of cosine curve. So we'll try and understand why that is the case. When you're visualizing it, remember, one of the major themes in Calc 3 is going to be try and take a 3D image and try and chop it up in some way into 2D images so that we can better understand it. So the idea is to look at shadows. So this is like Plato's allegory of the cave. Imagine you have a viewer who's tied to a chair and can only see some screen along the xz plane. So I've drawn that here. This is y equals 0. It represents the xz plane, the thing spanned by this axis and this axis. And that's all he can see. And there's some powerful light over here. Maybe it's the sun itself. And the point is doing its little, so remember, there's our little point, and it's doing its little dance through three-dimensional space. But he can only see the shadow that this casts on the xz plane. So this light casts a shadow. And as this point over here, let's see if I can do this. As this point over here, the legitimate real-life point moves, the shadow moves too, but he can only see the shadow. It's as if he has no idea what the y-coordinate is, but he's keeping track of the x-coordinate and the z-coordinate. So this guy is really seeing in the xz plane, this guy who can't see the y-coordinates but only the shadow of that point, he's seeing the formula x equal to cos t, comma z equal to, it was just t. So he's seeing cos t, comma t. Okay, and if you graph that, what does cos t and comma t look like? Well, if there's the z-axis, and then there's the x-axis, well, it's like z is, or x is a function of t, right? You would just say if z is the same as t, then that's like x equals cosine of z. And we drew something very similar in the previous video for 2D, and it looks something like this. It looks just like that kind of sinusoidal curve. So in other words, what are we saying here? Remember, this guy can't see the point itself, which is out here and has some interesting y-coordinates. He has no idea what's happening vis-a-vis the y-coordinate, but he sure knows what's happening to the shadow, the x and the z-coordinates. So he's looking at a shadow in the xz plane. That's all he can see. He's seeing the shadow. But it shows you that if you kind of take this legitimate 3D picture, and that helix that we have here, and you project it to the y equals 0 xz plane, so there it is again with the y stabbing us in the face, it looks just like a cosine curve. And isn't that picture a little bit lopsided? Sorry, it's a little awkward to kind of rotate these things. Isn't that just like the picture I drew here? Absolutely it is. But hey, how come he's strapped so that he can only see the x and z coordinates? You could have asked, well, wait a minute, what if he's strapped so he can't see the z coordinate of the point? That point is moving around behind him. He can't see that legitimate point. But again, he can see its projection, its shadow, because now there's a light. I guess the sun is back here now. He can see its shadow that it's casting on the xy plane. So he can't see the legitimate point, but he can see how the shadow is dancing. What would he see now? Well, he can't see the z-coordinate, but he can see that the x-coordinate and the y-coordinate are behaving like cos t, comma sine t. Remember, where I'm getting these formulas, I'm just going to the original formula and ignoring the variable that he cannot see. In this case, he can't see that last t variable, but he can see that x is equal to cos and y is equal to sine. And I've already drawn that in the previous 2D video. That literally looks like, so here he is, it's awkward because he's looking down at it. That literally looks like a circle. And that corresponds to when I had the z stabbing us in the eye, and it looked perfectly like a circle. And that's all he could move, sorry. Trying to get it look exactly like a circle, just like that. Okay? And finally, and I'll just leave this to you because I don't want to make the video too long, but you could imagine he's, sitting back here in his chair, and he's only looking at the YZ plane. What's he going to see? Well, he's probably going to see some kind of sinusoid because he's going to see y equal to sine t, comma z equal to t. So y equals sine of z or something like this. So it's going to look something like that. Okay, but again, you're just thinking of these as projections of the actual particle, which is moving in 3D space, onto some 2D plane, like this little shadow and allegory of the cave. So hopefully you can kind of visualize it and think about it with this picture, but let me jazz this up a little and actually have it graph, because we can do this. We can have it graph these things simultaneously. So I'm going to add the situation where x is equal to cos t, as it should be, and y is equal to, let's just say 0. So we're looking at the projection. When y is 0, that's going to draw this just in the xz plane, which is y 0. And if I recall, z was just equal to t. So now it's going to graph. Let's graph this and see what it looks like. Great, so it's a little bit harder to visualize here. Let me increase my plotting range so that we can better see this. Instead of going just from negative 180 to 180, let me go from negative 500 to positive 500 for my time variable. And let's see what that looks like. So there's our helix in blue, and it might be very hard to see this, but you can see that right now I have a little sinusoidal curve, and if you look at it, it's stuck at y equal to 0, and it's just on the xz plane. So they look, when the y is stabbing us in the eyes, they completely overlap the image, but when we look directly from above, you can kind of see that that green sinusoidal curve, it's a perfect little sinusoid, and it's just on the xz plane. Alright, there's something very similar if we eliminate only the x variable and we leave it on the yz plane. So let me draw that. Let's see how cool we can make this. So let me add yet another one. Alright, this time I want x to equal 0, so that we're looking at the yz plane, and y should have been sine of t. And again, z is just going to be t by itself. And I bet I'm going to have to, I'm going to graph it, and I have to adjust my t again, but it doesn't really matter here. Let me just zoom in a little, make this a little bit bigger. So you can see the blue curve is the legitimate helix. It moves around in 3D space. Notice that the green is on the xz plane. We saw that before, and it's a sinusoidal curve. And meanwhile, we have another kind of sinusoidal curve in red. It's trapped on the yz plane. And look at how the red curve is like exactly 90 degrees to the green curve, which makes perfect sense because the red is sitting on the yz plane, the green is sitting on the xz plane, and they're meeting at 90 degrees. So you can kind of see the shadow. The blue is the legitimate curve, and it casts a green shadow on the xz plane, and it casts the red shadow on the yz plane. Okay, so just to make the picture complete, let's add one more, and this time we're going to set z equal to 0, and we're going to look at the projection of all of this onto just the xy plane. So y is sine, did I do this right? Yep, sine of t. And then finally, my z is just going to be 0, so that I can see the projection. Graph that. So it's that last curve right there. It's that like gray looking curve. And it's just a circle, which makes sense because when I have the z staring us square in the eye, stabbing us in the face, you can't tell the difference between the blue helix and the gray circle. But you can see that gray circle is sitting on the xy plane. It's exactly horizontal. So you're looking at these three kind of perpendicular slices, not slices actually, but projections of it, shadows of it. And that's what the picture looks like. So it's fun to kind of toy around, but that's just showing us in much better drawings than I could. There's my gray circle. That would have been my red, kind of my red sinusoidal curve there. And then I think up here I had drawn my green one. That would have been the actual green one here. And then the legitimate picture is some kind of combination of all of them. So to understand and visualize the 3D parametric curve, my suggestion, try and just ignore one of the variables, set them equal to 0, look at just the xy plane or the yz plane or the xz plane, and see what kind of 2D shadow it's projecting and what that looks like. That way you can use your understanding of the 2D parametric plots to better understand what the 3D parametric plots look like.